modes, tags, I'll talk about tags and communicators, but modes is really, really the important thing. So I'll cover MPI modes, send, bsend, and send. I'm going to have to actually, I'll just, fine. I was killing some windows there so I don't get too many notifications. Send, bsend, and send. The meaning and use of message tags are rationale for all MPI communicators. Now, all these are commonly misunderstood, but it is essential for all programmers to understand modes. It's often useful to use tags, and certain cases benefit from exploiting different communicators, but really the focus of this talk is on the modes. So the modes are MPISend synchronous send, guaranteed to be synchronous. The routine will not return until the message has been delivered. So that's fine. We know what that is. So that's nice. We know what it does. But we saw in even a very simple example, such as the traffic model, where you're just sending and receiving data with a neighbor in a cyclic pattern, you have to worry about deadlock if you use synchronous send. It becomes an issue. So you might, well, why don't we use bsend, buffered send? It's guaranteed to be asynchronous. Okay, the routine returns before the message is delivered. The system copies the data into buffer and sends it later on. As I said, this is the only safe way that you can implement asynchronous send is for the system MPI library to take a copy of the message, and that's why MPI calls it buffered, to make that completely explicit. Now, MPISend, standard send, which is the routine which most MPI routines, most MPI programs use, may be implemented as synchronous or asynchronous. Causes a lot of confusion. So I think it's very unfortunate I have to talk about this detail on the first day of an MPI course. There are kind of three things which are unfortunate about MPI. A, the syntax for MPI init is horrible for C programmers. Char star arg v arg c. No, int star arg c, char triple star arg v is a bit disgusting. The fact that the status variable has to be an array in Fortran, but it's very easy to pass a scalar and your program crashes unexpectedly. But the really most unfortunate thing is the distinction between send, send, and bsend. But it is very important, so that's why I cover it here. So let's just kind of do a run through. So here I've got process A and process B, and time is going down the way. So I'm trying to run, time is going down the way. So we're starting at the top. And so process A is issues a synchronous. This is an abbreviated syntax, but it issues a synchronous issues. So it's probably asynchronous send. Sounds like asynchronous send. So MPI issues synchronous send to process B of the variable X. At that point, process B is running some other non-MPI code. And so what do you think happens here in this timeline? Anyone have a guess? A is waiting, absolutely. So A sits and waits in the send. So you're in the MPI library, it's sitting in the send, and it's waiting for something to happen. It's phoning, okay? It's waiting. So hopefully, in a correctly written MPI code, process B at some later time issues a matching receive. So process B goes, okay, I now want to receive from A into Y, my variable Y. And at that point, the data transfer happens. And there's two important points about the data transfer. One is that there's a synchronization in time. That's why it's called synchronous send, that at some point, both sender and receiver are talking to each other. There's a synchronization. And secondly, at least in principle, this data transfer can be done with no copying because they're on the line at the same time. Process B can say, you've got some data, could you put it here? And process A sends it. So those are the two important points about synchronous send. A, there is a synchronization in time, hence the name, and B, as a side effect, it is possible to implement this with no intermediate buffering. Then when it returns, when the send returns, what's the important thing? Well, in fact, when the send returns, you naively think it's really, really important that you know the data has been received. it's a bit of a subtle, but you don't really care the data has been received. Actually, you care that it will be received at some point in the future, but the fact it actually has been received at that point is not very important. What is important is the side effect of that X can be overwritten by A. That is really the important thing. When you do synchronous send, you call, I want to send X. When the synchronous send returns, you can overwrite the send buffer because the data has been delivered, okay? That's the important thing. X can be overwritten by A. When the receive returns, you know that Y can now be read by B. You know that Y has its value. But actually, it's a slightly subtle point, but at the sending side, yes, you know that the data has been received, but why do you really care? Because, I mean, process B could then go to sleep for half an hour for all you know. Actually, the really important thing is you know you can overwrite X. X can be overwritten by A. So that's kind of it, at least functionally important when you write a correct program. So let's talk about BSend. What would happen with BSend? Okay, process A. So BSend is an explicit asynchronous send. Okay, guaranteed to be asynchronous. So we start off the same. Process A calls BSend. Process B is in some running some other non-MPI code. So what happens at this point is the MPI library takes a copy and it returns immediately. Okay, so the important point is that you now know that X can be overwritten by A. So whenever a send operation completes, doesn't matter if it's synchronous or asynchronous, when it completes, i.e. returns control to you, the sender, you can overwrite the buffer. That's really useful, either because the message has been delivered or because it's been copied, but you can overwrite it. And then you carry on your merry way, okay? So MPI now has a copy of your message. At some later point, process B issues a receive. At that point, the data transfer happens. So there is no synchronization between sender and receiver, okay? Presumably, the buffer space is freed up. The receive returns and Y can be read by B. So we've achieved the same thing, okay? And it seems like it's a better process because there was none of this hanging around, okay? Basically, there's none of this hanging around. Process A doesn't wait, okay? So so you think here, right? I'd always like to do asynchronous send, but the question is, where does this data come from? Okay, where does this buffer come from? And it's a slightly technical point, but I didn't want to go into the details. But MPI has a number of requirements. If you're writing an MPI library, one of them is there's a requirement, and one of the requirements. Well, actually, I'll come back to it. I'm a bit premature here. So, receive is always synchronous. So actually, I could have drawn these diagrams if I went back. I'll just go back. This is one problem with animations. I could have drawn these diagrams such that process B issued the send first. Process B issued the receive first. Now, in that case, actually, the synchronous and asynchronous models are kind of similar because there's no waiting around in either case, because if process B issues the send first, the receive before process A issues the send, then it matches straight away and there's no hanging around. Process A for process B, they're already waiting. So I did it that way for clarity. So if process B issued receive before the B send was, then B would wait in the receive until the B send was issued. So if the receive happens before the send, then in both cases, if it's synchronous or asynchronous send, process B waits in the receive. So that's why I didn't draw it that way, because it doesn't illustrate the point. The important point is, where does the buffer space come from? Okay, where does the buffer space come from? Now, MPI is not allowed to use an infinite amount of resources. MPI has to have. If you ran a program and it ran out of memory, and you say, why does my program run out of memory? And the MPI library guy said, oh, well, I reserve a gigabyte of memory for buffered sends. And you said, well, I don't do any buffered sends. Okay, so I mean, what's going on? MPI says it is up to the user to provide this buffer space, which gives you control. So you can say, so there's a routine called MPI buffer attached. I don't cover BSend in any detail because it's kind of horrible. What you do is you allocate some memory, say a megabyte, okay? You allocate a megabyte and you give it to MPI. There's a routine called MPI buffer attached. You say to MPI, when I do buffered sends, explicit buffered sends, BSends, I've given you this amount of storage. This is where you store them, okay? That's where the space comes from. The problem is, can be quite difficult to bound that or calculate it, because the important point is that this point here, okay, when the BSend returns, okay, process A could issue another BSend, okay? Process A, in principle, could issue an infinite number of BSends before process B issues a receive. Now, in some programs, it's possible to rationalize. You can say things like, it's not possible for there to be more than 4 outstanding BSends. However, it is a bit tricky. And so, because what happens is if you want to use BSends, you, the programmer, have to supply MPI with some memory. If process B is having a particularly bad day and is very slow, process A could issue lots of BSends and overfill the buffer. And if it overfills the buffer, it will crash, because MPI says, look, you've asked me to do a BSend, you've mandated I have to do a BSend, but I can't because I've run out of buffer space because process B is very slow today, hasn't issued enough receives, and I crash. So if you use BSend, it can be quite difficult to work out how much space you need, okay? And if you get it wrong, you can get a program which runs 9 times out of 10 and sometimes crashes. Even if you can work it out, it's a bit nasty. So imagine that my messages are a megabyte, okay? And I know there can never be more than 4 outstanding messages from process A. So each message is a megabyte, there can never be more than 4 of them. So the maximum is 4. How big does the buffer need to be to store those messages? It's a bit of a trick question, but give me the obvious. So I know my messages are 1 megabyte. I can never have more than 4 of them outstanding at once. How much buffer space does MPI need? Why? Yes, yeah. Why more than 4 megs? That's a very good answer. It is the correct answer. You're absolutely right. Why do you think it's more than 4 megabytes? Heads, absolutely. So not only do you have to reserve 4 times 1 megabyte, plus there's some magic constant called MPI BSend overhead, which is the head. I mean, it's just horrible. Okay, so you're absolutely right. So it's really, really nasty. So here's the quandary that you face as an MPI library writer, or you'd like to use asynchronous sends all the time, but you can't guarantee to do it because in principle that could use an infinite amount of memory. So the rationale is we'll have a routine called send. Okay, so the problem is send runs the risk of deadlock. Okay, bsend is less likely to deadlock because it doesn't rely on there being a matching receive, and your code may run faster because you don't wait around, but the user must supply the buffer space. The routine will fail if this buffering is exhausted. So you can have programs which sometimes run and sometimes don't. Okay, MPISend tries to solve these problems. What MPISend says is, look, I will try and buffer it if I can. Okay, and this is a separate buffer. It's not the buffer provided by the user with MPI buffer attached. It's some internal buffer of some size provided by the system. Send will normally be asynchronous, but if the buffer is full, rather than failing, rather than saying, you told me to do a buffered send and I can't, so I'm going to crash, it says, well, you told me to do a send. I'll try and do a buffered send if I can, but if I can't, I'll become synchronous. So that's why MPISend has the choice. Now, in principle, MPISend could do synchronous sends on Wednesdays and Fridays and buffered sends on every other day of the week. That would be legal, okay? Or toss a coin. That would be legal. But in practice, it has the freedom to implement it synchronously or asynchronously. What it does is it says, right, I will send messages smaller than, let's say, 8 kilobytes, for example. It's a kind of standard number, asynchronously, but above that, I'll go synchronous. And so the MPISend routine is unlikely to fail right? Unlikely, so but it won't fail because it tries to be asynchronous, but if it runs out of buffer space, it reverts to being synchronous. But it could cause your program to deadlock if buffering runs out. So MPISend tries to give you the best of both worlds, but as a programmer, you always have to think maybe it isn't buffered. And so what people do is they write programs like this. Process A does send XB, process B does send YA. So process A is sending X to B, process B is sending Y to A, and then they do receives, okay? Now, if this were synchronous send, okay, if this were synchronous send, then it is guaranteed to deadlock, okay? Because they're both phoning at the same time, okay? That means if it's send, it might deadlock, and might is the horrible thing, okay? The worst program, a program that might crash is worse than a program that does crash because it's an intermittent thing, okay? So how would you fix this for this particular case, okay? How would you fix this problem? Write a program which would work correctly if send is synchronous or asynchronous. There's a way of doing it to make sure that the swap one, absolutely. So process A does send and receive, and process B does receive and send. So that's absolutely correct. Unfortunately, that doesn't generalize, okay? So in general, it's hard to do that. Let's think we're doing halo swapping to our nearest neighbors in a 3D grid, or even worse, some unstructured dynamic problem. So the real solution to deadlock is to use non-blocking communications. And I'll cover them tomorrow. So non-blocking communications are the correct way to avoid deadlock, the general way of avoiding deadlock. But the important point is a lot of people write code like this and they get away with it because they're sending small messages, but it's a very dangerous way to program. And most importantly, you don't have direct control over this internal buffer space. MPI can pick what it wants. And typically, it will reserve enough memory to buffer a message for every destination. It will say, look, I've got enough buffer space so that I can, any message less than 8K, I will buffer it. But that means it needs to reserve a buffer space for every possible destination. What that means is the bigger the program you run, the more processes you run on, the smaller the buffer space, the smaller the switchover tends to be. So the classic thing is people say, I've got a program that runs on my laptop. I run it on Archer. It doesn't work. Your machine is broken. This is often the case. They have assumed that MPISend is asynchronous. They have assumed MPISend is buffered, and that is not guaranteed. Okay, so it's a subtlety. So if the buffer is full at the send call, if some space is free, does this call stay sync? Probably. I mean, that isn't defined, but I would get yes. I would guess. That's an interesting point. You know, a really, really high quality MPI implementation might loop over and say, oh, I originally, well, in principle, it doesn't have to. In practice, it will, because what actually happens, I don't want to go into the details, but what for synchronous send, what happens probably is that at the moment you issue the send, MPI sends a little header saying, look, I've got a message for you. It's too big to send now, but it will come later. So it will already have sent the header indicating it's going to do synchronous send to the receiver. So in principle, it could switch, but in practice, it won't. I think that's the right answer. It will probably make the decision at send, at initiation. I don't have enough space now. I will switch to synchronous mode for that send. That's a good question, though. I suspect the problem is when it decides to go synchronous, it will have sent up a little protocol message saying that, and that's, it's a good question, though. So the solution either match sends and receives explicitly, as Michael said here, a couple of people said swap. So when we do the ping pong, which is this bandwidth test, we do send receive on one and receive send on the other, but that doesn't generalize. So for this course, you should program with send, because if you write an incorrect program with send, it will deadlock. If you write an incorrect program with send, it might run, and that's dangerous. So what you should do is you should develop your program with send, and then when you know they work, change all the sends to send, and it will it will probably run, and it will run fast. It is absolutely true that a program, if you convert a correct program written using send, should also work if all the sends are sends, because send is allowed to be send is allowed to be send. The converse isn't strictly true if you write a program with send and convert them all to sends, because you might be relying on, but in practice that's very rare. So my recommendation is develop program with send. That means if you have a deadlock problem, it shows up, your code stops working, so you fix it properly with non-blocking communications, which we'll talk about tomorrow. And then when you do a production run, you change all the sends to sends and it runs faster. Okay, that's quite a lot of stuff to take in. But are there any questions there? So it is, you know, whenever you program with send, you should think this send could be synchronous. Okay, would my program work if that were true? And MPI is trying to help you here, and it comes with a caveat. The caveat is, you know, buyer beware, it might still have to revert to synchronous, and then you have all these deadlock issues. So I don't know if there's any it's unfortunate that MPISend is so, a lot of people don't realize it's so complicated. You see a lot of incorrect MPI programs. I don't want to give a guess as to how many fraction of, not big packages obviously, but you know, self-written user code. So what fraction are technically incorrect? But it's, so if there are no questions on that, checking for messages. So somebody asked before, do I have to pre-allocate the buffer? I can't remember who it was. I hope it wasn't the guy who's having problems connecting just now. Somebody asked. So if you have a program where you're sending messages of arbitrary size, how can you receive them? Because you have to pre-allocate the buffer. Well, of course, what you really do is you just allocate a really big buffer and cross your fingers. But if you're a purist, what you do is use MPI probe. So MPI probe does everything a receive would do, but it's the same parameters as a receive, but without the receive buffer. So it's set, what MPI probe is saying, if I issued a receive here, what message would I receive? So the status is filled in, and the status tells you who the message is going to come from, what its tag is, but more in this case, often most importantly, how big it is. And then you can allocate the buffer and issue an MPISend. And if you issue an MPISend, it is guaranteed that it will receive the message that you probed. Careful with wildcards. If you do a probe with MPI any source, when you do the receive, you can't specify MPI any source because it might match a different one. So you have to specify the specific. You have to specify status.mpi source when you do the receive. Is that clear to people? There's a bit of a technicality, but if you do want to be able to legally receive messages of arbitrary size, which is surprisingly uncommon in MPI, but anyway, it does happen. Your standard modus operandi would be MPI probe, MPI alloc or realloc, and then MPI receive. Is that clear? So MPI probe, you shouldn't overuse it. You know, it shouldn't be your standard mode of receiving a message. Your standard mode should be a receive. But if you do really need to receive a message the alternative is to always send two messages. The first one says the size, the second, you should never do that, okay? That's a horrible thing to do because sending a message has an overhead and you don't want to double the overhead, okay? So if you are going to be sending messages of arbitrary size, don't do send an integer with the size, then send the message and do a double receive. Use probe, it'll be quicker. So I hope that answers the question about the, how do I have to pre-allocate receives? Yes, but you can work out what size they're. So yes, you can always be sure the receive message is the same as the one registered by probe. The caveat is if you receive with an MPI any source, when you do the receive, you can't do MPI any source. Again, you have to do status.mpi source. If you're going to be really trendy and mix OpenMP threading with MPI, you need to be even more careful because you have threading issues. And there's a special thread-safe MPI probe. But if you can guarantee, yes, that the message received by receive is the same as the one registered by probe, with the caveat on wildcards and a slight side case with threading. Does that answer your question? This is the one that catches people. Yeah. So tags, every message can have a tag. It's a non-negative integer value because a message from one source or another is FIFO. But I think of those being as well, they're not in a FIFO actually. So well, I'll mention it here. So no, it's an inbox. It's not a FIFO. That I covered that in some detail in the message ordering, but if I do a send of tag 1, I'll do it asynchronous. I'd send a message to you with tag 1. I send a message to you with tag 2. Okay. So in the inbox, well, the tag 1 message came before the tag 2. Yeah. If I do a receive with tag 2, I receive. It's not a FIFO because I can receive the message behind the tag 1. So the true statement of message order preservation is that if a receive matches multiple messages, then they will be received in the order they were sent. But it doesn't actually mean you have to receive them in the order they were sent, because you could receive with a different tag. I just don't really have time. And actually, I illustrate the message ordering with an exercise where I get people to stand up, and it's much. Maybe want to look at those message ordering things. So it's not a FIFO. Probe has to do clever stuff. But, well, receive uses the same matching rules as probe, put it that way. They match with exactly the same criteria, so it's guaranteed to match the same message modulo the wildcard issue. But it's not quite because they're a FIFO. That would be too simple. Is that okay? It's a very good question. Now, the tag has to be. Why do you think tag has to be non-negative? I can pass this value MPI any tag. Okay. I set you a home exercise to write an MPI library. Okay. So you have to write MPI receive. You have to be able to tell whether the user has specified a tag of their own or specified this wildcard value MPI any tag. What value do you think MPI any tag has? -1, yeah. It'll be a negative. So the reason that negative tags are, so yes, tag has to be a non-negative value, absolutely. And MPI, you could grep for it. I could actually, if I'm being naughty, I could. So I've just grepped for it in the source, and there it is. I mean, this, but you know, that's what it is in the implementation we happen to be using, which I think is Intel MPI. MPI actually only guarantees to support tags up to 32767, which is 2 to the, oh, I can't remember what it is, 2 to the 16 -1, something like that. Now, in practice, the real value will be higher than that, but it's not arbitrarily large. So some people, for example, will run a simulation, say you're doing a particle simulation, millions and millions upon millions of atoms or water molecules. Some people, when they send data for particle I, will tag it with I. Now that can be dangerous because the value for the particle tag can get up to the billions, and that can overflow. You need to be careful. You can, it's something to be wary of, but they can't be arbitrarily large. So if you're starting to use values in the tens or hundreds of millions, you have to worry. That's a problem because I've actually got the value here. I found it accidentally. On this implementation, the maximum value of a tag, MPI tag upper bound, is that number, which is 1,681,950,000. Okay, so it's about the biggest number you can store. It's 2 to the 31 or something. On your laptop, it's probably big. On Archer, it's only a few million. Okay, so people have been caught out by that. It's a technicality, but be careful. However, in practice, most people don't use tags, I have to say. Not everyone uses them. You have to specify them, but just set them all to 0 if you don't use them. Have some default value. Okay. They can be useful in this controller worker situation where I'm giving you guys work and you're sending it back to me. How do I tell you this is the last message you're ever going to receive? Okay. Well, what I would do is whenever I send you a message, I tag it. And I might tag it with 0 to mean you're going to get more, but I might tag it with 1 to say this is the last one you're going to get. So when you receive from me, from source 0, but with tag MPI any tag. When it comes in, you look at the tag and you say, oh, this is a tag 0, I'll process it and get more. Or it's the tag 1, it doesn't have any more work for me. So they can be useful, but in practice, in scientific and technical programming, it is actually useful. Unless you're using any tag, okay, I don't see the point in using tags, because unless you wildcard, to receive a message, you need to know what the tag is. So you can't convey any useful information. So it might make you feel uncomfortable, but there are situations where tags are useful with wildcarding because they can convey extra information without an extra message overhead. And I have occasionally used them, but in practice, I haven't used them that much. And unless you're using wildcarding, they're really not of any use, because the receiver has to know what the tag was to receive the message in the first place. So I don't know if that's so. A lot of programs don't use tags. But you have to specify a valid value. So you have to just set it to 0. Okay, that would be a standard thing to do. Oh, I'm in the wrong window. Communicators. All MPI communications take place from the communicator. A communicator is fundamentally a group of processes. It does have more information. We'll see tomorrow they can have structure. A communicator can be a structured grid of processes, but the fundamental thing it defines a group. There's a predefined communicator called MPI Com World, which contains all the processes. There's another one called MPI Com Self, which contains just you. A message can only be received within the same communicator in which it was sent. Unlike tags, it's not possible to wildcard on COM. So if you want, and there's a couple of uses for common usages for user-defined communicators, which I'll cover. The first one is the one MPI Com Split. You can split MPI Com World into pieces. So there's a routine called MPI Com Split. I haven't given the syntax here, but you can look it up. But it allows you to split a communicator into subcommunicators. So I could, if I run on 7 processes, I have MPI Com World, this rank 0, 1, 2 up to 6. I could do an MPI Com Split, specifying the correct parameters, and I might call the communicator called Com1, which has rank 0, 1, 2, and 3 from Com World, and Com2, which contains rank 4, 5, and 6 from Com World. But note, in Com2, they have different ranks. Your rank goes between 0 and the size of your rank is specific to communicator. So you have a rank in Com World, you have a rank in Com1 or Com2. And by definition, your rank in Com2 can't be the rank the same as the rank in Com World, because Com2 is only size 3. The ranks in Com2 have to be 0, 1, and 2. So there's a remapping there. So if you're going to play around with multiple communicators, you have to be careful to remember multiple ranks. Now, your rank in Com World is the most important because it's globally unique. Okay, there is only one rank 0 in Com World, but there's, within these subcommunicators, you can have different ranks. So it guarantees that messages within here. So if you want these guys to do one calculation and these guys to do another one, you want to effectively split your machine in software. Then you would use subcommunicators. Some people might say, well, I won't bother. I'll just send messages here and use tag 1, and send messages here and use tag 2. The problem is this guy could issue a receive with MPI any tag, and the messages could get mixed up. So tags aren't enough to guarantee separation of messages. If you want messages to be guaranteed not to interact with each other, you want separate communications worlds, you have to use communicators because you cannot wildcard on a communicator. And this allows you to write library routines. So the other thing you do is you can make a copy of Com World. If you're going to write a library routine, a parallel library routine, like a sorting routine or a fast Fourier transform, it's clearly going to send lots and receive lots of messages. How do you make sure that the sends and receives in the library routine don't accidentally match a send or a receive from the user code? Because remember, the user code might have a receive from any tag. So the only way to guarantee that a library can safely send messages which aren't intercepted either maliciously or by accident by the user is to have a separate communicator. Now that could contain all the same processes as COM world. So if you want to create a new communicator, it's not enough to say new COM equals COM world. That's just copying. That's just a reference to the same thing. You use a routine called MPI Com duplicate, MPI Com dupe. So what a well-written parallel library routine will do is that in its setup phase, it will create its own private communications world, possibly just a copy of COM world, but logically a separate communicator. So you have separate communications worlds. The user cannot intercept the library messages if the library keeps the identity of the new communicator secret, which is easy to do. You can't just reserve tag values because of wildcarding. So those are the two uses of communicators in general terms. Does anyone have any questions about that, about communicators? I haven't given you the syntax for MPI Com split, but it's you just so that's yes and no. So so you will have each process will have a variable called COM. Let's want to create a subcommunicator here, okay? I've been a bit naive saying COM1 and COM2. Each process will have a variable called subcom, which will be an integer in Fortran or a type of a variable of type MPI Com, and you will call MPI Com split. And on ranks 0, 1, 2, and 3, COM will refer to COM1, and in ranks 4, 5, and 6, COM will refer to COM2. So no, the names aren't global. It's a bit difficult to. I'm trying to find it. It's a bit like each of these opening a file. They all have their own file pointer, so they have their own local file pointer, but they could all point to the same file or different files depending on what value they have. I don't know if I explained that very well. So the names aren't global. It's when you create them, all of the COM values, they are private variables. The value you have of communicator is a private variable, but all of these guys here will have a value which refers to the same global communicator. I don't know if that's a good way of. So you store the private variable, but they do refer to the same value. Yes, the value is global. In some senses, the value is global, yeah. How the MPI library does that is up to it, but I mean, yeah. There is a global concept of a communicator. A communicator is a global concept. You get a handle to it which refers to this global concept, but actually the value is global. Because it's returned to you. You say to the MPI, please create a new communicator and give me back its value, and you don't decide it, it just gives you back one. So it will pick up, it will have a table of free values. Does that make sense? You don't say I want a communicator wants to be value 53, it gives it back to you. Yeah, you get, so your communicator is just this one of these handles. It refers to some internal data structure which MPI maintains. Is that okay? Yeah, fine. So it is a subtle point. That was a good question to ask. So summary, why bother with all these send modes? Answer is a little complicated, but you have to understand SSend and BSend are clear. They map directly onto the concepts of synchronous and asynchronous, of phone calls and letters. Send can be synchronous or asynchronous. MPI is trying to be helpful here, give you the benefits of BSend if there's sufficient system memory available, but not failing completely if buffer space runs out. In practice, this leads to endless confusion. It's the right thing to do. The amount of system buffer space is variable. You cannot, now there will be probably some magic environment variable you can check, but it's not the same as the MPI buffer attached memory. It's an internal thing set up at MPI init time. Programs that run on any one machine may deadlock on another. You should never assume that send is asynchronous, okay? So if someone says, my program only works if I set this magic variable, MPI internal send buffer size equals 50K, they have an incorrect program, okay? We can come back to this, but it is a point which I bang on about rather a lot. What are the tags for? If you don't need them, don't use them. Perfectly acceptable, set all tags to 0. Some people tag messages with the rank of the sender, or that's not the style I like, but set them all to 0. I would not use the value 0, because the unfortunate point about receive is that the tag and the source values are right next to each other. It's easy to get them mixed up. So I would have some global value called MPI default tag value, or default tag, or tag, or something like that. So it's in there as a something which stands out. Question: can I just use MPI Com World? Yes, many people never create new communicators. However, it is bad practice to write, although in our simple test programs we'll do this, it's bad programming practice for any number of reasons to write MPI Com World anyway. First of all, it's a horrible, ugly, long, constant, and line wrapping in Fortran is a hassle. But also, you may write your program thinking, oh, this is only ever going to work on MPI Com World, and then in a few years you think, well, actually, I'd like this program to be able to work on a communicator which isn't Com World. If you've hard coded MPI Com World everywhere, it's going to be a nightmare to fix. So you should get into the habit of doing MPI Com, or an integer in Fortran. Com equals MPI Com World. That is not duplicating Com World. That's just this is a reference to the same Com World. Okay, and then MPI Com rank, MPI Com size. Okay, but use com. It's a much nicer, more elegant value than MPI. So this code looks more elegant, is more readable than having this horrible MPI Com World, and it's more general, because in the future you could change this to be com equals some subcommunicator, and your program works magically on this subcommunicator. So that's a bit of advice. So that lecture ends rather abruptly, but that's the end of their end of the lesson. So that's my explanation of send, BSend, and SSend. Very few people in MPI use BSend explicitly. It's very rare to see explicit BSends. And in fact, so I've talked about the nitty-gritty. If I were an MPI library developer, I would say the reason you use send is you should not be telling MPI whether to do it synchronously or asynchronously. You should let MPI decide what it thinks is the best. And in certain situations, synchronous send is faster than asynchronous, because for really big messages, like gigabytes, taking a copy is a very slow process. Okay, so having synchronous send is actually quicker, because it can match them up and do a sender to receiver transfer with no intermediate copying. So that the party line is you should use send because it allows MPI to choose the most efficient method. The real thing is it tries to be asynchronous, but it needs to make a buffer, and it can't have an infinite buffer size, so sometimes it gives up and uses synchronous. So I don't know if that's clear. So that's the end of the lectures for today. The exercise is just to go back to the Pi exercise. There are quite a few additions to it. If you do finish it, and I wouldn't expect you to be able to in the time, but if you do or work on it overnight, then there are a couple of other exercises. The ping pong exercise, which you could also do. There's this by hand broadcast stroke scatter. And the nice thing about those is that they illustrate how to send messages of more than one, and also how to send not just an array, but the internals of an array. No, well, so it's a technical point. Can I use it with explicit in the buffer? I think that by default, if you don't call MPI buffer attach, the reserved buffer size is 0. So I think if you run a program and even send a single integer with MPI BSend, if you haven't done a buffer attach, I think the MPI will say run out of buffer space. In practice, that's what it tends to do. I think it may be mandated, I can't remember, but no, you can't guarantee. I have seen MPI implementations where if you try to send a single integer without having done MPI buffer attach, it says, I don't have any buffer space. You haven't given me a buffer attach. Also, I should say the model is not MPI buffer attach, MPI BSend, MPI buffer detach. The model is MPI init. You say to MPI buffer attach 4 megabytes. So look, that's, and then you just run with it. It's not meant to be something you just. It's meant to be something you set at the start of the program. So MPI, you can detach and reattach and do all kinds of stuff, but the model really is that you say at the start of the program, look at MPI. if I do BSends, here's 4 megabytes where you can store them. And if you're confident that you will never need more than that buffer space, you're happy. That you're safe. Does that make sense? But again, programmatically, the advantage of using BSend is you don't have to worry so much about deadlock, but actually non-blocking communications, which we'll cover tomorrow, is the correct and more elegant, more general way of doing that. And the difference between asynchronous and non-blocking, yes, if I write COM1 as MPI1, COM2 equals MPI1, then COM, yeah, that's correct. They are just the same thing. They're just the same thing. It's like opening a file, and you have are you Fortran or C programmer? Yes, you do. You open a file and you call it file pointer. If you do fp1 equals fp, fp2 equals fp, they're different variables. They point to the same file. Okay. If you want, yeah, fine. So they're references, and so I don't want to get, yeah, that's absolutely correct. Yes. You can deliberately confuse people by doing things like that. You can write programs which appear to refer to different communicators but don't. So you need to be careful with your naming conventions, because if you did that, but there are reasons why you want to do it, but you could actually you could write a very obfuscated program if you did that, to be honest. But yes, you are correct. So that's I'll be here to myself, and I think Julian is still around. Yes, apologies, Julian, I didn't see you on the list there. Great. Me and Julian will be around until sorry, I'm having a slight problem with my chat window. Yeah, we'll be around till 5:30. Apologies, that's a bit late in Europe, but we will start again tomorrow. I'll put up a slide. So, you know, the first thing I will do tomorrow, if you look at the time, I will go over the Pi exercise in some detail. Hopefully that'll make more concrete some of these topics. And I will also tomorrow, I was pleasantly surprised at how many people classify them as modern Fortran programmers. I will illustrate with a specific example tomorrow how to program in the modern way with Fortran 2008. Now, the reason I don't teach it separately is A, I haven't updated the slides, but B, all you do is you copy the C syntax. With the Fortran 2008 interface, the C and the Fortran syntax are modulo a few underscores and capital letters the same. So it's really, really easy to do the 2008 interface. It actually just looks like C, but I'll show you tomorrow with an example of how to do that. I think that's everything. Yeah, so I'll put up a slide and we'll be around here till. Thanks, everyone. I hope you enjoyed today. I'm doing this format of Thursday, Friday, and then a gap till next Friday. I had considered doing a week gap in between, but it's, I don't know. I thought if we were doing mostly face-to-face courses like we normally do and some online courses, that would be the option I'd use. But because we can only do online courses because of COVID-19, if we stagger them like that, then we have an awful lot of courses running at the same time, and it can get complicated to manage with accounts and things. So I don't know. I would be interested in people's opinions on this format of solid days with interleaved practicals, rather than spread out kind of, you know, across different days. It's something we're learning. So okay, so but the technology seemed to work well today. Again, we do have, I would like to try this tomorrow, that, you know, if someone has an MPI, a Pi example that works, I would like to try screen sharing if someone would like to, because that's something I'd like to check that it works. I've heard people saying that screen sharing can be slightly problematic at scale. We've got 25, 30 people here, so that, you know, it would be something I've not experienced that, but we have people internationally here. We have somebody from Canada, I think, and people from all over. I don't know if the Canadian person is here. It's going to be awfully, would have been an awful early start for them. I would like to try that tomorrow, because it's a model which, in this course, you're doing set practicals, so I know I've taught this course enough times that if someone has a problem, I've probably encountered it before, I can just answer it. It's not because I'm brilliant. It's just because I've seen it before. It's because I'm old. But if we were doing a course where people were developing their own code, or a tools course where people all brought their own code, it would be essential to see people's individual screens to debug their particular problem. And so screen sharing with obviously I'm sharing my screen here, but screen sharing with attendees is something I would like to experiment with. We can maybe do that tomorrow morning, because we're definitely around here for the next half hour or so, and speak to you again. You'll hear me again tomorrow at 9:30 British Summer Time.